Hello, my name is Rob Reynolds. Welcome to section 3.6, derivatives as rates of change. Remember, the rate of change simply means the slope of the tangent line. When we're finding the slope of the tangent line, we're finding the derivative. Well, in this section, the only thing we really need to learn is that the slope of the tangent line, the derivative, is also known as velocity. That's the rate of change. And then the second derivative is acceleration, sometimes denoted like this. Remember, when you're finding the average velocity or acceleration, those are just derivatives. So let's first of all talk a little bit about the difference between distance and displacement. The distance around this block would be, well, twice the length plus twice the width, or 12, because 2 plus 4 plus 2 plus 4 is 12. But the displacement doesn't talk about how much you've traveled. It talks about how far is the overall change. How far did you move from beginning to end? And if you started at the end, ended at the same spot, then your displacement is 0. So average velocity, so you may ask, well, what's the difference between velocity and speed? So velocity does care about the direction, where distance doesn't care. If you're going to the right or going to the left, it's just the distance. So velocity, to find it, we take the derivative, and then and you could use this limit process, which we learned in 3.1, but we have short techniques, power rules and stuff. So the slope of the tangent line today is the velocity, is the definition. So let me give you an example here. We have a police car or a police station, and he's going along a straight east and west freeway. At noon, we're going to say at time 0, the patrol car leaves the station heading east. And they have a function down here to kind of show you what's going on. We're going to determine what's going on. Position function of the car is given by that function. East is positive and west is negative. So first of all, they say describe the location of the patrol car for the first 3.5 hours of the trip. So in part A, he's going to be traveling, let's see, positive. Looks like the slope here is positive, and we decided that positive was heading to the east. So looks like he's heading east, or it's heading in the positive direction until it kind of hits right here. It looks like slope is 0. So I would say somewhere between 0 and 1.5, the patrol car is heading east. And then it looks like he's at rest in this time frame. So between 1.5 and 2 o'clock, he's not moving, not going anywhere. And then he starts driving back, because now the slope of the tangent line is negative. So I would say he's heading west between 2 and 3.5. It looks around 3.5. Now, this is an interesting little piece of section down here, because it looks like he went further to the west than where he started, and that's why he's a little bit lower. So he ends about 20 miles west of where he started. Well, how did I come up with the 20 miles? Well, the 20 miles is denoted by this down here. So if this was 0, he's 20 miles to the west of his start position. So that's part A. Part B says calculate the average velocity between 0 and 2. So at time 0, well, let's just write it as an ordered pair. At time 0, he hasn't moved anywhere. And then at time 2, we got to figure out where his position is, and at time 2, it looks like he's up at 80. Oh, so they gave me 2 points. Let's go use the average velocity definition. It's just slope, y minus y over x minus x. So f at 2 That's the 80. So f of 2 is 80 minus 0 over 2 minus 0, which is just 40. And that's 40 miles per hour for part B. And then part C says calculate the displacement between 3.5 and 2. So really, I just want to find the change. That's the displacement. So I'll just take f of 3.5 and subtract off f at 2. And the function evaluated at 3.5 is around negative 20. That's, of course, going all the way out to 3.5 and coming down here. There's the negative 20 that we talked about. And then f at 2, we decided was 80. And so I'm about negative 100 miles for the displacement, the change that he's made. At what time is the instantaneous velocity greatest when the car travels to the east? So I think they're talking about where the slope is the greatest, because that's velocity. So we examine the graph, and it doesn't look like slope is greatest down here. Looks like it's pretty steep here. So in section A, that's not very steep. B is pretty steep. C is pretty steep. So then it starts leveling off again. Do you see how it's going down? A, B, C, D, E. So it starts pretty flat. It ends pretty flat. So somewhere kind of in the middle, I don't know, somewhere between here and maybe here. So this represents like a half an hour afternoon. So maybe from like 12:30 to 1 o'clock. Looks like it's pretty steep in this region right there. I'll highlight it in blue for you. So there's the instantaneous, where that's the greatest slope, highest number. And at what time is the patrol cars at rest? I think we discussed that. It's at rest between 1.5 and 2, which is 1.5 hours after noon if it started at noon. So 1.5 hours after noon is 1:30 to 2 p.m. And so here's the author's explanation. He might have done a little bit better job. Feel free to read through that. B, C, D, and E. Good thing you can pause the video. So again, the only thing you really need to grab from this is the velocity is the first derivative. The speed is the absolute value of the velocity. The velocity can be positive or negative. The speed has to be the distance from 0. It doesn't care about the directions. And acceleration is the second derivative. So if you can grab, speed is the absolute value, that might be a new definition for you. Example number 2. So in example number 2, they gave us another function, and the first thing they say is determine when the object is stationary. Well, if the object is stationary, that's where the velocity is 0, and of course the velocity is the derivative. So I'm going to take the derivative of t squared minus 5t and compute the derivative of that, which is 2t minus 5, and lo and behold, set that equal to 0, because that's when it's stationary. So that happens around 5 halves, or about 2.5. So time is about 2 hours, 2.5 hours. Then it's moving to the left from, well, I might need to do a little bit of reading here. It says assume positive values correspond when the function is positive to the right. So we want to go left. So let's set this function, the velocity function is less than 0. That means it's going to the left. So that means t is less than 2.5. So there's 2.5, everything less than it over here must be moving to the left, and then vice versa, or you same process, but just 2t minus 5 would be greater than 0 every time you're over here, where well, I'm between 2.5 and 5, so there's there's the answer from the right, and then the answer from the left. I could say, well, it doesn't look like it's defined over here, so between 0 and 2.5. Part B starts asking about acceleration. So all I have to do is take the derivative of the derivative. And the acceleration is going to be 2. So notice that acceleration is a constant. It's constantly accelerating at the same time. And then part C, describe the motion of the object. Well, I think we kind of did that. At time 0, he's at 0. So, and then at 5 halves, he looks like it's at rest. So S at 5 halves, he's resting because that's also a 0. Well, when he moves to the left, that's negative. That means that what? He's decreasing his speed. And then, of course, moving to the right, or positive, that means he's increasing his speed. Let's see how the author described this. That was positive directions to the right, increasing speed. Oh, good. And then, yeah, during the time interval. Oh, there it is. Negative direction, it's decreasing speed. All right, so they even graphed then the velocity function. So let's look at example number 3. Find the velocity and the acceleration. Oh, that's nice. The velocity is just the first derivative. So negative 32t plus 64. That is the velocity function. And then the acceleration is just the derivative of that derivative. So negative 32, and we'll say that's the acceleration. So I've got 2 functions. What's the highest point above the river that reaches the stone? So if it's thrown up, oh, this is a negative. Oh, I think I have the graph already graphed under here. Here, there's better. Negative. So if it's negative 16t squared, there's the highest point. So all I have to do is find out where the slope equals 0. So for part B, I'll just set the derivative, which is negative 32t plus 64. I'll set that equal to 0 because I know that's going to be the maximum and the highest point. So solving for t, I get 2. So after 2 seconds, I can see that from the graph as well. It's at its highest point. And of course, you can find out how high it is if you just take that 2 and plug it back into the function and evaluate negative 16 t squared plus 64 times 2 plus 96. Or you could guess left, guess right, guess on, and actually calculate that. I think that's probably close to, I don't know, we'll find out on the next slide, 166. But then part C says, what's the velocity when it strikes the river? So it strikes the river when the function equals 0. And I'm thinking that I might be able to divide everything through by 16. How about negative 16? Every term, both sides. So t squared minus 4t minus 6 is 0, and then maybe that factors if it doesn't. Well, I can use the quadratic formula or bust out my calculator, guess left, guess right, guess on. And I think it turns out to be around 5.16. We'll throw out the time, negative 1.16, because that doesn't make any sense over here. So about 5, and you can see that that corresponds pretty close. You know how to find roots, take the and calculate the 0. Oh, this must have been 160. I guessed 166. All right. So this slide is talking about the average rate of growth, and you can just see that's the slope y minus y over x minus x. And then the derivative, instantaneous slope, is the derivative. So average growth, we're going to find the slope between these 2 points. And so I'm going to do, so here's my p function. We're going to let time be 0 at 1995. So so let's see. So at 2000, t is, oh, they've defined it for me. T is 5. T is, so I just do p at 10. That's the y value minus p at 5. That's y sub 2 minus y sub 1 all over 10 minus 5. So I'll just go to the function and evaluate it. And I'll leave that up for you, but I think you know how to do that. Where they talk about instantaneous rate of growth, then I'm looking for the derivative. And the derivative is t plus 70.8. And then I could evaluate that at any point. Well, a 2006 minus 1995 means evaluate this after 11 years. And so you just plug that in. 6 times 11 plus the 70 is around 137. And then part C starts talking about find out where it's positive. What does the graph tell you about the growth rate? It's positive and it's increasing. And part D asks be p sub 20. So let time be 20. So go to the function and evaluate that, and that's around 2.6 billion. And you could read through example number 4 and find out how the author described that. The last thing I want to say before I close this video is average cost is you take the cost and divide by the number of units that you've sold. And so that's divided by X. And then marginal just means the derivative. Marginal cost, marginal profit, marginal revenue, all means just find the derivative. So if you take in a business class, those are business terms, or two really good definitions. Average cost, you just divide by, you take the cost and divide by the number of units. That'll be your average. And then remember, anything marginal just means find the derivative. And there's, of course, some examples of that, which I'll leave you with this example to go through and check to see if you could find the derivative. And then the average cost, remember, you just take the function and divide by X, and that gives you the average cost function. If you have questions, feel free to email.